Hey IB, welcome back to the new year 12. So we're starting in the middle of chapter 16, and we have specifically 16D.1. So we're only going to be talking about horizontal and non-horizontal points of inflection and testing for concavity, and we'll continue with D.2 in the next video. So right now we've talked a little bit about concavity and just what it generally means. So anytime that we're looking for concavity, we're looking at the shape of the curve. So is it shaped upward or is it shaped downward? That would be the other option, concave down. So for this first graph, just x squared, familiar graph, just looking at the curvature, you'll notice that the gradient is very, very negative. The gradient of the tangent line is steep, negative, and then it gets a little bit less steep here. And then at the vertex, it is completely horizontal. So our gradient, or our derivative, winds up being 0. And then as soon as we pass that vertex, the gradient of the tangent line gets steeper, and then in a positive direction, and then steeper yet in a positive direction. So we change from a negative steep gradient of your tangent line to 0 to a positive steep gradient. So what that means for us, because we can tell by looking at the graph how to find the concavity. We know this is concave up, but how do we tell the concavity from the actual equation? So if we actually did the math and we found the derivative, 2x, if we graph 2x, we'd have a linear function with a gradient of 2. So it would look something like this, relatively steep. So there's our gradient. And if I did my sign diagram, it's negative until 0 and then positive after 0. So negative y values, positive y values. So my sign diagram would show that I have negative, positive. We already discussed that if your first derivative sign diagram has a negative and a positive value, it says that your original graph was decreasing and then increasing. So decreasing and then increasing. So now, what can our second derivative tell us? So my second derivative of 2x is just 2, so it winds up just giving you this horizontal line. And if I did my test, my second derivative test, so instead of substituting in a number into the first derivative, let's substitute into the second derivative, and notice how you're going to get 2 no matter what you sub in, because you can't sub anything in. So you're going to get 2 no matter what, which is positive. This positive sign in my sign diagram reinforces the concavity of the curve. So by getting a plus, that means we get a concave upwards curve. So the first derivative tells us about increasing or decreasing, and the second derivative tells us whether we are concave up or concave down. All right, so we have a local minimum at some value of a if your first derivative equals 0. Your first derivative at a will also equal 0, but now we're noticing that your second derivative at that point is going to be positive, so greater than 0. If you have a second derivative that's positive, like this sign diagram shows, then you're going to have a concave up scenario, which means you have a local minimum. Similarly, if we look at negative x squared, which is a concave down graph, and at a, we'll say this is a right here, your gradient is 0, and you change from a positive gradient of your tangent line to a negative gradient of your tangent line. So let's see what the math shows us here. The first derivative would be negative 2x, which means I now have a negative line, negatively sloped line. And now I'm going to use my first derivative to test. So negative 2x, if I substitute in a value less than 0 and greater than 0, I'm going to wind up saying, well, this one is positive, this one's negative. Again, I'm above the x-axis, I'm below the x-axis. So what that tells me is that I was increasing until 0 and then decreasing after 0. And it might be 0, it might be whatever this a value is, just for this one happens to be at x equals 0. So we do agree the graph is increasing until the maximum and then decreasing. With the second derivative test, I'll get -2, which is just a horizontal line at -2, which would mean that no matter what value you substitute in, you're going to wind up with negative values. So what this tells me is that I have a concave down curve. All right, and that just reinforces what I knew from looking at the graph. So this piece of calculus is really helpful just to reinforce what you're noticing in the actual diagram, but also how can I figure out what the graph will look like if I don't have a picture of it or if I'm not using my calculator, which is exactly what we're going to have to do as well. All right, so now we would solve an equation for the derivative equals to 0 to find what point we have a maximum, or a point of inflection. And if your second derivative comes out to be less than 0, then we know that you have a concave down scenario, which winds up meaning that you have a maximum. Okay. So taking a look at some of the vocabulary that we just went over, a point of inflection is any change in concavity. All right, so when a graph changes from increasing to decreasing, that's not a point of inflection. That is a change in increasing, decreasing, which would be a maximum or a minimum, right? That's a change in direction, but not curvature. If we have a change in curvature, that means we switch from being concave down to concave up. So for this example, that change happens somewhere about here. For you to find your points of inflection, so if I want to find my point of inflection, I'm going to take the first derivative, but then I'm going to take the second derivative as well, because the first derivative is going to give me my horizontal points of inflection, which are when your tangent, or your gradient of your tangent, is 0. So that's when your first derivative is equal to 0. However, your stationary points come from when your curvature changes, which is when your second derivative is equal to 0. So now we are going to do the same test for both the second and the first derivative in order to find everything we need to graph accurately. So for example, if I was graphing -x cubed, which is what this one looks like, you have a tangent happening right here, and this is a horizontal tangent line. So since it is a horizontal tangent line, the gradient will equal 0. So in other words, I would have found it if I set my first derivative equal to 0. So if I took my first derivative, -3x squared, and I wound up graphing that, okay, if I set that equal to 0, I'm going to find that 0 is actually where this changes. So I have an increasing and a decreasing graph. So my first derivative is going to be, reinforcing what's happening in my original graph. So this would actually be negative. But remember, your first derivative just tells you decreasing and increasing. So this is actually decreasing and then continuing to decrease. So if you look up at your original, I decrease, and then something happens, which I found here when I set my first derivative equal to 0, but then I continue to decrease. So this is called a horizontal point of inflection. Horizontal point of inflection. Okay? If I take my second derivative, I just get -6x. So I get a very, very steep negative line. And if I did my sign diagram for my second derivative, I'd wind up with positive, negative, which would mean I went from being concave up to being concave down. So you just have to analyze what you're getting in your sign diagram, and it should reinforce what the graph really looks like. So I am decreasing and then decreasing, but I went from concave up to concave down, so that means I have that horizontal point of inflection, also known as a stationary inflection, because your first derivative was equal to 0 there. All right, so in summary, to test for a horizontal point of inflection, I'm going to take my first derivative and set it equal to 0. And your second derivative would also wind up being equal to 0, is really what's going to happen there. Then last but not least, what happens if I don't have a horizontal point of inflection? What if it's a vertical or non-stationary point of inflection? So something like this curve here. It's still a cubic, but I now have a very obvious change happening in concavity about halfway through at this x equals a point. I have a change from moving concave down to concave up. However, the tangent line is not horizontal, so it's not a stationary point. It is a very, very steep negative tangent. So we call that, it's either going to wind up changing from and being a vertical tangent, otherwise it could just be a very, very steep negative and then switches, right? So it goes through that vertical point. So if you guys are looking at this graph here, and I have my function x cubed plus 4x squared minus 4x minus 16, and I wind up taking the derivative, I get 3x squared plus 8x minus 4. So just based on this graph here, what would we guess our sign diagram for the first derivative would look like? So if you'd like to pause here and try this on your own, you're welcome to. So before b, the graph is increasing, then decreasing, then continues to decrease, and then increases again. So what's happening here is I am increasing, so I'm going to have to be above the x-axis until b. Negative, meaning I drop below the x-axis. Still negative, so that means I'm still below the x-axis. However, I'm about to switch to be positive after c. And that way, I have mapped my original graph to my first derivative. If I apply this to my second derivative, it's 6x plus 8. Go ahead and pause here and see if you guys can figure out what your second derivative would look like. So based on your original function, again, we're concave down, down, up, up. So my second derivative would show down, down by being negative, negative, up, up by being positive, positive. So basically this is going to be negative until a, and then positive after a. And remember that every time you take the derivative, you wind up dropping one power. So you wind up with a cubic to start, a quadratic as your first derivative, and then a linear function as your second derivative. So in summary, if you'd like to test for a vertical point of inflection, so we're going to test all of our functions this way, your first derivative, you're not going to find it there. You're not going to find anything, your vertical point of inflection there, because you set your first derivative equal to 0, and you're not going to find it. So you have to take your second derivative and set that equal to 0, then you'll find your vertical point of inflection. So first derivative set equal to 0, you'll find your horizontal points of inflection, and then your second derivative, you'll find your vertical points of inflection. In summary, this is a fantastic visual that I think your textbook provides to show you when you actually are looking for turning points. So turning points being changing from increasing to decreasing or decreasing to increasing. When you can use your horizontal points of inflection, so you're not changing, it's not a turning point necessarily, you are changing slightly, but you're still decreasing or still increasing. So you're looking at those monotonic functions. And then you do so find those points where the changes occur with your first derivative set equal to 0, and then your non-horizontal inflections when your second derivative is set equal to 0. In preparation for class, go ahead and try this number 4, and we'll start here when we see you guys next time. Have a great night.